Okay, welcome to lecture here. We're continuing on chapter 7, which is solutions. Okay, so we started talking about solutions. Grab some things here. There we go. And a couple of reminders here, as we talked about last time, a solution is really made up of two things. When we talk about a solution, it's also those things that we see sort of in formulas or equations that has the AQ symbol next to it, usually indicates a solution. It's made up of the solute. The solute is the smaller part of the solution. And it's made up of the solvent, which is the larger part of the solution. And both of those together is, again, what makes up a actual solution. So as we talked about last time, a lot of times the actual solvent is water. So water a lot of times is a solvent. It doesn't always have to be water as the solvent, but it's a very good solvent for a lot of things, especially ionic and polar things. It's a very good solvent for. And we talked about the idea of sort of solubility, and solubility, if something is soluble in each other. So if it's a solid in a liquid, the solid would dissolve. And that would be soluble. Obviously, if the solid doesn't dissolve and it stays there, it'd be insoluble. So it'd be insoluble if it didn't dissolve. We also could talk about sort of solubility of two liquids. So when we mix two liquids together, again, if they do mix together, they would be soluble and look sort of like this. All looks like one liquid. If we had two liquids that we mix that are insoluble in each other, we would see sort of different layering sort of happening if they're insoluble in each other. And sometimes that's called miscible when we talk about kind of liquids and liquids, or immiscible if you're talking about two liquids that really don't mix. So they're really sort of an important factor that helps us determine whether or not, two things really will sort of mix together or not mix together. And a lot of that has to do with a very common sort of phrase that we talk about when we talk about sort of solubility, and it's the idea of like dissolves like. And basically what that means is, in order for things to sort of mix together and sort of interact well with each other, we really are dealing with those intermolecular forces, which means that if we get two things that have very similar intermolecular forces, they're going to probably mix really well. If we get two things that really don't have very similar intermolecular forces, which again are those forces that basically act between one molecule and another, they're not going to be able to interact well with each other, and we will not get things to be really soluble in each other. So what that really means is, if you take something that's ionic, it will be pretty much soluble or in things that are polar. And again, that's kind of like what happens when we take something like sodium chloride or some type of ionic compound and we dissolve it in water. Water, which is polar, has a positive and negative side. The ions, when they go for a swim, is positive and negative, and basically the waters just surround all the ions, basically. And that's what helps it really dissolve, and it's able to interact really well with each other. We also can get things that are polar and polar. Those things interact really well with each other as well. Again, in this case, they probably both are using either some type of dipole-dipole interaction with each other. They may be using hydrogen bonding with each other, but they have some way to interact really well with each other. And that also means that, if we take something that's nonpolar, for example, and mix it with something that's nonpolar, it also will mix really well with each other. Again, they both are nonpolar, which means in terms of sort of intermolecular forces, they're both going to be using really dispersion forces as their kind of main way to interact with each other. And they are able to interact with each other really well. So all these guys here are the idea of like dissolves like. All these guys would be soluble in each other, again, because overall they all kind of share similar intermolecular forces, and that allows them to interact really well with one another. It's really, as we talked about last time, kind of when you cross over, if you try to take something that's polar and non-polar and kind of put them together, they're not going to interact very well, and they typically are going to be insoluble. And that is because, again, really coming back to our intermolecular forces, something that's polar is going to try to do some dipole-dipole interaction. Maybe it will try to do some hydrogen bonding, while something that's nonpolar is pretty much stuck with dispersion forces, which are those really temporary weak type forces. So as they try to interact for each other for the short period of time, and I think maybe I did like an example, like oil and vinegar salad dressing or something like that, for a short period of time, they both technically could kind of use some dispersion forces to interact with each other, but that's the only way they can, and that's going to be relatively a weak interaction, and eventually they will sort of separate out from each other. And it's very much like what we see when we dump some oil in water. Typically the oil will then float on top of the water. Again, no real long way to interact with each other. And that's different than what we have up on top. Everybody is using here kind of the same interaction. So they have, over a long period of time, an ability to maintain that interaction. And that's why, again, they are soluble in each other. While when you try to go kind of to things that are very different in terms of their intermolecular forces, over the long period of time, they really don't have a way to maintain that interaction as you would in a sort of polar and polar, or nonpolar and nonpolar. We finished up, I think, talking about what's on this slide here. And these are really solubility rules. And we could use these rules to help us decide when we're, say, writing an equation or a reaction. If we put two things together, would we expect it to be a solid or to be basically aqueous or a solution? So when you look at solubility rules, if it's something is said to be soluble, what that means is, like these examples we did at the end there, it will get the aqueous symbol. And they're basically solutions. So no solid, everything's dissolved. It's like not a pure liquid, but it's basically a solution. If you look at the solubility rules and something is insoluble, that means it will get like the solid symbol. And that means that when you mix those things together, you would expect some type of solid basically to form. So again, we could just kind of, excuse me, if we take some sodium chloride plus some, let's do some lead nitrate like we have up on top there. And this will make some sodium nitrate and some lead to chloride in this particular case. And what happens when we look at these solubility rules, we can look at sodium chloride. As soon as we see the sodium, that is group 1, as we talked about last time. Group 1 is soluble in everything. There is no exceptions. So again, we would expect this guy to be aqueous. Lead to nitrate, we do see the nitrate part is here as well, and that is also soluble in everything. There's no exceptions. So we would expect this guy to also be aqueous. And, to probably balance it would be the right thing to do there. Put some T's in there. When we come to the other side, we got some sodium nitrate. Again, looking at sodium tells us it's going to be soluble. You really don't have to look any further. You can look at the nitrate part of it as well, which on our chart is also going to be soluble. It will get the aqueous symbol. Here we look at lead and chloride. Chloride is soluble in everything except for silver, lead, or mercury 1. And in this case, this is lead. So this would produce us a solid. So this guy here, again, would be the solid that would be produced based on the solubility rules. So basically what we would be doing in this case is we would be taking two solutions. when you mix those solutions together, pretty much all the ions are floating around in the solution. The lead ion and the chloride ion will want to come find each other and basically make a solid, and you would see this solid basically form. Any questions on any of that stuff that we talked about last time? Okay. So then we will sort of continue on here. Let's see here. So let's talk a little bit more about sort of solutions and some solubility here. So as we talked about here, reviewing just a second ago as well, essentially that is the main idea there, that things that have similar ways to interact with each other through those intermolecular forces, be it dipole-dipole, hydrogen bonding, dispersion forces, they're definitely going to be really soluble in one another. And again, it just gives them a way to interact with one another over a long period of time. And that's going to help them basically dissolve essentially. The solubility of a solvent does depend on temperature. So, you know, when you try to dissolve, say, a solid in a liquid, there is a limit to how much you could actually get to dissolve. And that limit is based on temperature. And typically speaking, if you increase the temperature, you do get a sort of a larger solubility of like a solid in a liquid. That's why sometimes they'll say if something doesn't dissolve, heat it up. When you do that, you're adding a lot more energy, it's allowing more things really to dissolve. So at higher temperatures, we have a larger solubility of a solid in a liquid typically. At lower temperatures, we have a lower solubility of a gas in a liquid. I'm sorry, a larger solubility of a gas in a liquid. And that's for this reason here. If we have a liquid and we have a gas molecule kind of flying around, when we lower the temperature, this gas molecule is going to start to move slower. So it's going to basically stay in that liquid part a lot longer than if we were at a much higher temperature. If we were at a much higher temperature, that gas molecule may just kind of shoot right out of the solution much, much faster. So at a lower temperature, our gas molecule is going to be moving slower. Because it's moving slower, it's going to be in the liquid part for a longer period of time and thus be mixing with the liquid part for a longer period of time. Solubility of gas does depend on pressure. This is at a higher pressure, we have a larger solubility of a gas, and that has to do with you know, what we talked about with Boyle's law, P1V1 equals P2V2. As the pressure goes up, the volume goes down. So at higher pressures, we have a much smaller volume, and a much smaller volume means all of our gas molecules are sitting in a much smaller area, which means just by that process, we are definitely having a lot more mixing happening of those gas molecules. In addition, at higher pressures, we have a larger solubility of a gas in a liquid. So for example, there's a lot more gas molecules in a liquid at very high pressures. This is also sometimes what is referred to as like Henry's law, and that is like the soda can idea. When you have a soda can, it is under a lot of pressure, and before you pop the top, there is a lot more of the CO2 molecules dissolved in the liquid part. Once you have popped the top on your soda, you see several things happen. You see usually some fizzing coming out the top. When you do that, you obviously release the pressure. That's going to allow the CO2 molecules to escape the liquid part, and you actually gave it an escape route out the top. So that's what you're seeing, all that fizzing that comes out of the top of the soda can, and the CO2 is able to leave obviously at that point. That's also why, right, when we leave our soda can open for a while, when we come back and we take a drink, kind of flat. And that's because we lowered the pressure, released all that CO2 and gave it an escape route, and all that carbonation, basically the CO2 left, and we're left with sadly flat soda at that point. Maybe we drink it if we're really thirsty, I suppose, and give it a go, see what happens. Now, as I mentioned, there is sort of a limit to how much you could get of a solid to really dissolve in a liquid. And if we have too much solid in a liquid, or we've hit that point where pretty much we could get all of the solid to dissolve for a particular liquid, that is what's known as a saturated solution. So a saturated solution is a solution where we have hit basically for that temperature, because it is based on temperature, the maximum amount of solid that will dissolve in a liquid. So if you have, somebody says you have a saturated solution, it is probably still a solution at that point. But you're right exactly at that point where if you decide, I'm going to dump some more solid in there, it will no longer start to dissolve. So you'll just start to get the solid kind of building up on the bottom, because you pretty much hit what is sometimes referred to as the saturation point, that point where that's the maximum amount of solid that you could get to dissolve. Now, if you haven't hit that point, you have what is known as an unsaturated solution. Unsaturated solution will still look like a solution. The difference is, in an unsaturated solution, if you dump more solid in there, it will actually dissolve, and it will dissolve. And it will continue to dissolve if you just keep dumping solid in there until you reach a saturated solution. So you can dump some more solid in there, it will continue to dissolve. You can dump more solid, it will continue to dissolve. At some point, if you keep doing that, you will hit the saturation point and a saturated solution, and obviously no more will dissolve at that point. So saturated solution, maximum amount you can dissolve at that point. If you continue to put solid in there, no more is going to dissolve. Unsaturated solution, you have not hit that point. You could continue to put solute or solid in there, and it will continue to dissolve until you hit the saturation point. And at that point, obviously, it will not dissolve. Other ways we could kind of describe solutions, we can describe solutions as concentrated or dilute. In a concentrated solution, we have a very high concentration of solute. In a dilute solution, we have a small amount of solute. So what that means is in a concentrated solution, they're sometimes called stock solutions. We have a lot of the solute kind of dissolved in that solution. It may not look red, obviously, but we'll just use that for a diagram of there. Now, a lot of times, as we'll talk about, when you make a diluted solution, you essentially take a little bit of that concentrated guy and, you put it in there. And then what you get is, I'll just kind of lightly, we got a little bit of that solute in there, a lot more water or something like that has been added to it. You take a little bit of the strong guy out, you add something like water, for example, and we end up with basically a diluted solution. Kind of like when you get the big gulp drink with all the ice in it, you take a few drinks, you go into school or whatever it may be, right? And you come out a few hours later and the drink's been sitting in your car, all the ice is melted, right? It is much, much more diluted than when you started with in terms of your soda. You probably still drink it, give it a shot, go, hey, it's only been 3 hours. It can't taste that bad. You take the drink and go, well, maybe it can taste that bad. Maybe I shouldn't do that. So concentrated solutions, very, very high concentration of solute, the stuff dissolved in it. A dilute solution, a lower concentration that's basically dissolved in it. All right, so let's talk about then electrolytes. Electrolytes are substances that when they dissolve, produce ions and conduct electricity. And when they do conduct electricity, the reason they're able to do that is the presence of those positive and negative ions that are floating around in that solution. Kind of helps create the circuit, kind of keep everything moving, electrons moving, and will be able to conduct electricity really well. And there's a few different types of electrolytes. The first type is a strong electrolyte. And when you have a strong electrolyte, it 100% breaks apart into ions. So if you take some sodium chloride, that's a solution of sodium chloride, even though we call it a solution of sodium chloride, what is really happening in that solution is you have 100% these ions present. You have absolutely no sodium chloride units still together in that solution. So this creates a lot of free ions really quickly. And because it creates a lot of free ions, it's known as a strong electrolyte. If you take something like hydrochloric acid, which is another strong acid and strong electrolyte, it also 100% will break apart into H plus and Cl minus. And because essentially in that solution, you got pretty much everybody on this side, you got a bunch of ions, it will conduct electricity really well. Usually, again, if you look at a light bulb, a very common sort of experimental light bulb that has some electrodes hooked up to it, and you kind of stick it into a strong electrolyte solution, you will see the light bulb go off very brightly. And again, because it can conduct electricity really, really well. Now, on the other hand, if we have a weak electrolyte actually will mainly stay together. So in solution, for example, if you take something like hydrochloric acid here, which is a weak acid, in solution, you mainly have this guy still here, the HF unit still together. But it will produce a little of these guys. So it'll produce a little bit of these ions. And because it's able to still produce a little bit of ions, it's able to conduct electricity. But not as well as a strong electrolyte. A strong electrolyte is a really good conductor of electricity. So if you kind of go back to the light bulb example, if you were to kind of put the light bulb with the electrodes in, it would go on, but it would be very dim. It wouldn't be super bright. It would be very dim, almost like you would look out and go, looks like the light bulb's about ready to kind of go out. But it would be dim, and it's able to conduct this electricity because it's still able to produce a few ions. So the difference between these two is one is a really good conductor of electricity and one is an okay conductor of electricity. And the main difference that you can see is usually weak electrolytes will have arrows that head in both directions. So is that like equilibrium type reaction that we talked about in a previous chapter where the reaction heads in both directions. And that is sort of a key thing to look at in equations. If you see those arrows heading in both directions, you do know it's a weak electrolyte. And that's different than a strong electrolyte. A strong electrolyte, it is a one-way arrow heading towards the product side. So if you see a one-way arrow heading to products and you see ions on the product side, you could probably assume that it's a strong electrolyte. If you see a reversible arrows heading to products and reactants like we have here, and you see ions on the product side, it is probably a weak electrolyte. Again, strong electrolyte will conduct electricity really well. Weak electrolyte will still conduct electricity, but nowhere near a strong electrolyte. That leaves us the last one, which is referred to as a non-electrolyte. In a non-electrolyte, what we essentially will have is something that will dissolve, but will not produce any ions. And because it does not produce ions, it does not conduct electricity. So, for example, we all know sugar. Sugar will dissolve if you put it in water. Sugar is pretty much made up of carbons, hydrogens, and oxygens, which means those guys will share electrons and covalently bonded and will not produce any ions. Because you have no ions that are being produced, if you put the light bulb into that solution, you will get no light. So the light bulb will not go on in that case. And the main reason it will not go on is because, again, there is no ions that are present in that solution. Although it may dissolve, you got no ions. So a good way to kind of recognize that in terms of equation form is you got kind of both of the same things on each side. The only difference is the state change. It goes from, say, solid to aqueous, or it dissolves. But we basically have both things on the same side. That's the same. No ions being produced on the product side. And that's a very good way to know that it's a non-electrolyte. Any questions on electrolytes there? By the way, water, pure water, is a really bad conductor of heat and electricity because water is covalently bonded. There are no ions present, so it doesn't conduct electricity very well. So with that being said, clearly the water that comes out of your tap is not pure water. They actually put ions into the water that comes out of your tap to purify it. And it conducts electricity really, really well, the water that comes out of your taps and stuff like that, because there's actually a lot of ions that are present in that case. So don't go, blow dry your hair in the shower because you will get electrocuted. But if you have technically pure water, H2O, nothing else in it, it actually is not a good conductor of electricity. And again, one more time warning, the stuff coming out of your pipes is not pure water, so please don't electrocute yourself. A reminder as well that perhaps if I take sodium chloride that's in the solid form and I stick my light bulb with my electrodes in there, the light bulb will not go off. And that's because in the solid form, the ions are together, they are not floating around. What you need for an electrolyte to conduct electricity is essentially you need those positive and negative guys kind of floating around in the solution. So it's not until we put some water in there with it to help it actually produce those ions free of each other that we get something that will conduct electricity. So, if you took solid sodium chloride and stuck the light bulb thing in there, it would not go off, or shouldn't. You take that same sodium chloride, put some water in it mix it up, get it to dissolve, put that thing back in. Now you have a strong electrolyte. So again, ionic compounds need that water to break apart from each other. As we might have talked about a little bit earlier in this chapter as well, that water basically surrounds those ions and it prevents them from coming back together in the solid state, and also kind of gives them movement and allows them to float around and move around in the solution. So again, if you have an ionic compound that's not dissolved, you wouldn't expect it to conduct electricity. But if you take an ionic compound and you dissolve it and produce those ions, you would expect the electricity to definitely be conducting. All right, let's see. So talking about the light bulb, here's some pictures of that. Here up on top, we have sodium chloride, again, in solution. And when we put an electrode with a light bulb attached, we see a very bright light comes off. That's our strong electrolyte. Again, the way you could really kind of recognize that is you will have, a one-way arrow and ions on the other side. This is a weak electrolyte. You can kind of see it's kind of dim, the light bulb when it comes off. And again, the way you could really recognize that is if you're looking at the equation like HF that we have here, you're going to have the arrows heading in both directions, and you're going to have the ions also being produced. So again, because it does produce a little bit of ions, we're able to conduct electricity. But if you could kind of see, it is mainly the HF unit still present, but we have a little bit of ions floating around. And again, that little bit of ions is enough to help conduct electricity. And lastly, here's our sugar. Again, it will dissolve, but no ions. So this is a non-electrolyte. And again, the way you could really recognize that, you can see the bulb doesn't come on, is, for example, if you look at the equation, for example, one way is obviously we have two of the same things, just different states, but obviously on this side, no ions being present is a good way to identify that as a non-electrolyte. Any questions on electrolytes there? Then let's talk about equivalence. Equivalence is oftentimes a way that body fluids, especially IV bags, for example, are sort of given in terms of concentration of solutions. And the equivalent of a ion is basically equal to the charge. Yeah, so to answer your question about that, if we just go back real quick here. So a weak electrolyte will remain both ions and molecules exactly. So when we look at an equation like our HF, the majority of what you actually have floating around that solution is the whole thing still together, but you still produce a little bit of these ions that are floating around. So you are correct, kind of like what it shows here. You have basically everybody still floating around that solution. And that's different than a strong electrolyte. You have 100% these ions floating around. So if you look in this picture of sodium chloride, there are all the sodium ions by themselves, the chloride ions by themselves. There's no longer any sodium chloride units still together in a strong electrolyte because they 100% broke apart. And that's why a strong electrolyte will conduct electricity a lot more, because it produces a ton of more free ions that are floating around, as opposed to like our HF in the middle here. where the majority of what you got floating around is still the whole unit, which is not producing ions, but you do get a little bit of these ions being produced, and that's why it's still able to conduct electricity. You're welcome. So equivalence, again, an equivalent is a way that we could kind of represent sort of the concentration of ions in solution. And it is really based off the charge. So for example, if we had a potassium ion in a solution, we could really come up with a conversion factor, and we could say for every 1 mole of potassium, we get 1 equivalent. And where did I get that 1 equivalent? I got it really from the charge. And when we're talking about equivalence, it doesn't really matter if the charge is positive or negative. It actually just matters the actual number. So this is a +1 charge, and that's where the 1 equivalent comes from. So for example, if I had sulfur with a -2 charge, I could say in 1 mole of sulfur or sulfide, I have 2 equivalents. Again, the 2 comes from the actual charge. Doesn't matter if it's positive or negative. And really, in most cases, what we will use this for is really like a conversion factor. We could say in 1 mole of potassium, there is 1 equivalent, or in 1 equivalent, there is 1 mole of potassium ions. And we could do the same thing for this guy and write it. So a lot of times IV bags and things like that are given in units of what are sometimes referred to as equivalents per liter, or sometimes they're given in what are known as milliequivalents per liter. And that milli conversion is kind of the same conversion as what we would do with like 1,000 milliliters equals 1 liter. There would be 1,000 milliequivalents equals 1 equivalent. So kind of the same type of conversion factor that we do. So a lot of times we will do these things sort of just kind of converting units into sort of equivalents per liter or milliequivalents per liter. So let's take a look at a couple of examples to just kind of see how we get there. So for example, if we had a solution here that was 0.025 moles per liter of sodium sulfate, and we wanted to figure out what the equivalent per liter and the milliequivalents per liter of both ions are in this particular case, we would want to do just really sort of a conversion sort of problem. But first, what we would really want to figure out is if I take a solution that's made up of sodium sulfate, I want to really figure out what I get in terms of ions. So if I have a solution of sodium sulfate, when that guy breaks apart, he's going to break apart into 2 sodium ions and 1 sulfate ion. So I basically get a 2-for-1 sort of deal here, okay? Now, when I look at each of these, I could come up with my equivalent relationships for each of those ions. So we're going to be looking at each of those ions sort of separately. We're going to be looking at the sodium ion and the sulfate ion. So if I do the sodium like I did on the other side, I could say in every 1 mole of sodium ions, there is 1 equivalent of sodium ions. And again, that comes from the charge here. So the charge is +1, so there's 1 equivalent. I could also, for my sulfate, say for every 1 mole of sulfate, there is 2 equivalents of sulfate. Again, the 2 is coming from the actual charge on the sulfate. For both of those guys, we could write 2 conversion factors, and we'll get to kind of using them here in just a second. But the first thing I want to do is I'm going to look at just the sodium ion first. So I do have to do a little bit of conversion here, because when I start with this guy, and if I start with the 0.025 moles of sodium sulfate per liter, I am not interested in the whole thing. I am only interested in the sodium part. So I need a relationship that gets rid of the entire thing to the sodium. And we can actually use the formula to help us do that. And it's kind of just like stoichiometry here. We can see that for every 1 mole of the whole thing, I get 2 moles of just the sodium ion. So I'm going to do that little conversion part first. For every 1 mole of the entire thing, I get 1 mole of just the sodium ion. Or actually 2 moles. I should actually do the right number. That would probably be better. We get 2 moles of the sodium ion. Again, the 2 is coming from right here, and the 1 is coming from here. So what that's going to do is really convert the moles per liter, which is really molarity in a unit of concentration, into what the concentration is of just the sodium ions. And if I do that, I will get 0.05 moles of sodium ion per liter of sodium ion. So again, this first part here is just to get us to just the sodium part. Now that I have it in just the sodium part, I can now use my equivalents and my relationship up here to do some conversions. So I'm going to get rid of the moles and try to figure out how many equivalents there are. So we know that for every 1 mole of sodium ions, I get 1 equivalent. The moles will cancel, and that's going to give me 0.05 equivalents per liter of sodium ions. And this would be the equivalents per liter of sodium ions that are floating around in that solution. And like I said, a lot of times they ask for milliequivalents. So we will do that conversion here. Again, in 1 equivalent, there is 1,000 milliequivalents. And if we do that, the equivalents will cancel, and we will end up with 50 milliequivalents per liter of the sodium ion. So the 2 answers here for sodium ion would be 0.05 equivalents per liter and 50 milliequivalents per liter for our sodium. Any questions on that calculation right there? So that takes care of the sodium. We want to also do the same type of calculation for our sulfate. So it's going to start very similar. We're going to start with our 0.25 moles of the entire thing per liter. Now, when we look at the relationship between the whole thing and sulfate, it is a 1-to-1 relationship, which means in 1 mole of the whole thing, I have 1 mole of sulfate. Again, this is going to get rid of the whole thing and get us into just the sulfate. And that would give me 0.025 moles of sulfate per liter. At this point, I now can use my relationship for sulfate and equivalents. 1 mole of sulfate is 2 equivalents. So we can do 1 mole of sulfate is 2 equivalents. The moles will cancel, and this will give us 0.05 equivalents of sulfate per liter. And we could then convert that into milliequivalents using the same conversion. 1 equivalent is 1,000 milliequivalents. That will get us 50 milliequivalents per liter of sulfate. So same 2 answers here. And you may notice that when we talk about this solution, the sodium sulfate, and we talk about its concentration in terms of the ions, it is 0.05 equivalents per liter sodium ions. It is 0.05 equivalents per liter sulfate ions. They're exactly the same. The milliequivalents per liter of sodium ions is 50. The milliequivalents per liter of sulfate ions is also 50. And what that is because when we put an ionic compound together, if you remember, the goal is to make sure that we end up with an overall charge of 0. And by canceling out that charge to 0, what we're essentially doing in terms of the charge of everybody that's floating around is we're making equal charges of both the positive ion and negative ion in terms of its concentration. So whenever you do the equivalents per liter or milliequivalents per liter for two ions in the same solution, they should end up with the same concentration. They always should end up, the positive guy and the negative guy should always end up as the same number. Question on that calculation there. All right. Why don't you try the second one there, see what you come up with. Let me just rewrite it on the next page. 0.0125. So why don't you try this guy here? See what you come up with. What we're looking for is what we just did there, the equivalents per liter and the milliequivalents per liter of both the potassium ion and the carbonate ion. So give it a try, see what you come up with. Okay, so let's take a look at it together, see how we're progressing on it. So first place where I really want to start is to figure out when we break apart this potassium carbonate, what we get. And we do get 2 potassiums, and we do get 1 carbonate ion that is present. Now, in terms of our relationship here, we know for potassium, for every 1 mole of potassium ions, we do get 1 equivalent. Again, the charge, the number. We also know for every 1 mole of carbonate, we're going to get 2 equivalents. Again, charge doesn't matter, but the number does here, so it's going to be 2. So again, we're going to use those as conversion factors to figure out the concentration of each of these ions. So we do need to kind of go from the whole thing to each one. So if we start with, for the potassium, again, for the whole thing here, for every 1 mole of the entire thing, we get 2 moles of potassium. And that comes from here, 1 to 2 relationship. And that will tell us that we have, we got there 0.0250 moles per liter of potassium. We then can use our relationship here to go from moles per liter to equivalents per liter. And in this particular case, it happens to be a 1-to-1 relationship, which makes the math easy. Again, using that relationship, for every 1 mole of potassium, we get 1 equivalent, given as 0.025 equivalents per liter of potassium. And using our conversion factor, 1 equivalents is 1,000 milliequivalents. That will convert us into 25 milliequivalents per liter of potassium in this particular case. So for potassium in this solution, it would be 25 milliequivalents per liter, or 0.025 equivalents per liter. And since this is an ionic compound, the answer for carbonate will be the same, but I'll show you the calculation here just so you can see it. We go with 0.0125 moles of the entire thing over liters. When we look at the entire thing to just the carbonate ion, it is 1 mole of the entire thing gives us 1 mole of the carbonate. And that also comes from the formula, so 1-to-1 relationship there. That's going to give us 0.0125 moles per liter of just carbonate. Now we can convert it into equivalents using our equivalents per mole conversion. And this is how we get it now to the same number. And every 1 mole of carbonate, there is 2 equivalents because of the charge. And that gets us to our 0.025 equivalents per liter of carbonate. And if I do the 1,000 move, we'll convert it into the same number going that way as well. So again, you can see in an ionic compound, it's a good way to check yourself to make sure you didn't mess up the calculation. Those numbers should always be the same for those guys when you're calculating equivalents per liter or milliequivalents per liter. Question on that. There are equivalents. Again, you can see from this table, we find that conversion from the charge. So 1 equivalent. Charge is +3, 3 equivalents, -2, 2 equivalents. Again, in terms of determining the equivalents, which really you're just going to use as a conversion factor. It doesn't matter if it's positive or negative. Really what matters is the actual number. Any questions on that there? Okay. So now what we're going to talk about then is actually some other more usable concentration type units. The first one is mass percent. The mass percent is sometimes abbreviated as percent m/m for mass to mass percent. It is what the name implies, grams over grams. So it is the mass of the solute divided by the mass of the solution times 100%. Now, the important part in this guy is actually the bottom one, because the mass of the solution is made up of two things. It's made up of the solute, which is the smaller part, and the solvent. And it's very common in these type of problems that you are given this information separate from each other. So you do want to make sure that you add those together. It wouldn't matter. It would probably, if there was one of these questions on the exam in terms of the equivalent question, it would tell you what units to give it, either equivalents or milliequivalents. So it would probably tell you, hey, give it in equivalents per liter and milliequivalents per liter, or it would tell you which one to do it in. If it didn't specify, you technically, I guess, could do it in either one, but it most likely will specify what units to look for. So in terms of our mass percent, again, people always miss the bottom part because they always just want to put the solvent by itself. So again, you want to make sure you get both of those. And it is very, very common that, like I said, that, they're separated. So why don't you take a try at one here? Solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. Calculate the mass percent. So calculate what the percent mass to mass would be. So take a couple minutes and see what you come up with. Okay, so let's take a look here and see. So we're trying to determine the percent mass to mass, which means we need the mass of the solute divided by the mass of the solution times 100%. So when we're mixing this together, we're taking 2.5 grams of calcium chloride. That is much smaller than 50. So that means that our calcium chloride here is our solute. The water here is only our solvent. So when we go to put this in, we would take the 2.5 grams divided by, we need to actually add those together. 2.5 grams for our solute, plus the 50 grams for our solvent, and that together will give us the entire solution. So again, very common, these guys are sort of separated, so you want to make sure that you do add those together. And I think we do get the 4.76, so 2.5 divided by 52.5 times it by 100, 4.76. Now, in terms of sort of the units, basically most people will go percent, and they will put m/m to indicate that it is percent mass to mass. And sometimes they will also put the name of it there as well, or the formula. So 4.76% mass to mass calcium chloride solution. Question on that one, where any numbers came from? Okay. So why don't you give the next one a go, see what you come up with. Concentrated hydrochloric acid is 37.2% by mass HCl. What mass of HCl is contained in 35.5 grams of the concentrated hydrochloric acid solution? Okay, so let's take a look at it. So again, we're obviously dealing with percent mass to mass, which is our mass of solute, divided by the mass of the solution times 100%. So in this particular case, we're given the mass percent, which is 37.2. So we do have the percent mass to mass, which is 37.2%. We also have the mass of the solution, which was given to us. And the mass of the solution is 35.5 grams. So we're really looking for the mass of the solute. So there is sort of a couple ways you could do it. You could actually just plug and chug into this equation, since you have everything but the mass of the solute, and you could come up with the answer. You could also approach this more as like a conversion factor. So when it says you have 37.2% by mass hydrochloric acid, you could turn that into really a conversion factor, because what that means is mass per mass. So if you assumed 100, which is usually what we do when we're dealing with percentages, we could say that there is 37.2 grams of HCl in 100 grams of solution. Or we could do the conversion factor the opposite way. In 100 grams of solution, there would be 37.2 grams of HCl. Here, I just took the percentage and assumed that we had 100 because that keeps the numbers the same. And I could turn it into really two conversion factors that I could use. And you may want to do that because we do know the mass of the solution is 35.5. So I can approach this as more of a conversion factor sort of calculation. So we have 35.5 grams of solution. I could use the conversion factor on the left here, which would give me 37.2 grams of HCl and 100 grams of solution. Grams of solution will cancel and leave us with the grams of HCl, and I believe it is 13.2, like I see there in the chat box, which is good. And you will get 13.2 grams. Now, you could do it that way. You could do it by plugging it into the equation. The truth is, it's the same calculation you're doing either way. You're just kind of setting it up more like a conversion factor, which may be easier to sort of recognize the units. But again, you could plug and chug into the original formula. It's the same math. You come up with the same sort of formula. So any type of percent concentration, you really can convert into a conversion factor. You could assume 100, and whatever it is would be that many grams in 100 grams of solution. And sometimes it's maybe just easier to kind of see the conversion that way, kind of doing it more like a conversion problem rather than plugging it into the formula and rearranging. Math-wise, it is the exact same math you're doing either way. But again, sometimes it's visually a little bit easier to kind of see it in that sort of approach. Question on mass. There's also a couple of other percent concentration units that are commonly used. So here's another one. This is what is known as percent volume to volume, like the one they use for alcohol, percent by volume. And it is very similar. It also is sometimes abbreviated percent V to V, which is volume to volume. It is the volume of solute divided by the volume of solution times 100. The difference here is usually they don't break up the solute and solvent here. So usually they just give you the solution's volume. So you don't have to worry too much about the bottom part here like you do on the mass to mass one. Usually this is a lot of times milliliters over milliliters. So in terms of the units, milliliters over the milliliters. So if you had a 3.25% volume to volume potassium chloride solution, you could say that you had 3.25 milliliters of potassium chloride in 100 milliliters of solution. Or you could turn it into a opposite conversion factor, 100 milliliters of solution, 3.25 milliliters of KCl. So again, works really the same way as percent mass to mass, but deals with kind of volume over volume relationship of those two things. And the third sort of percent concentration is mass to volume percent. And that is percent M over V. That's what the M over V stands for. Percent mass to volume, kind of grams over milliliters, essentially, like density. We don't usually use these sort of units here. We usually use just a percentage, but it is the grams of solute over the milliliters of solution. Again, since the bottom is the solution, usually you're given that as the whole number, not broken up in solute or solvent. Same idea as before. If you had 3.25% mass to volume potassium chloride and you wanted to kind of turn it into a conversion factor, you could assume 100. And what that would mean is you would have 3.25 grams of potassium chloride and 100 milliliters of solution, or the opposite conversion, 100 milliliters of solution on top would give you 3.25 grams of KCl. So again, works the same way. Usually when we kind of give the answer on this one, percent M/V is what we would usually give. Again, not usually, we usually won't leave the units like grams per milliliter. Not necessarily wrong in this case because they really won't cancel out, but usually it's more given as a percentage type number. All right, so why don't you try one here? What is the mass to volume percent of Br2 in a solution that's prepared by dissolving 12 grams of Br2 in enough carbon tetrachloride to make 250 milliliters of solution? Okay, so let's take a look here. So we're taking 12 grams of Br2. We're looking for the percent mass to volume here of Br2. Br2 is our solute. It is the smaller amount. Our solvent in this case is actually carbon tetrachloride at 250 milliliters. So really, we just need to plug into here. It is the mass of the solute, which is our 12 grams, divided by the volume of solution, which is our 250 milliliters, times 100%. And I believe you do get the 4.8% mass to volume of Br2 in this particular case. And again, like I said, we oftentimes will kind of get rid of those guys and stuff like that. Yeah, you should probably follow the sig fig rule. So just looking at these two numbers here, that has two significant figures. This guy also has two significant figures. You probably wouldn't look at the percentage here in terms of sig figs. So basically you have two sig figs divided by two. Probably should end up somewhere around two sig figs when it's all said and done. Yeah. Other questions on that? Okay. So why don't you try one more here and see what you come up with. Oh, by the way, before we move on from this, this is a nice example as well of what we were talking about earlier. Here, the solvent was carbon tetrachloride and not water, and that's because of two things that we talked about. When we have Br2, that is a nonpolar molecule, right? Which means if I try to put that into water, which is polar, they are not going to mix. They're going to float on each other. Basically, the bromine will be on top, water will be on the bottom. So when we take something like carbon tetrachloride that looks like this, I won't draw out all the electrons, but if you remember from geometry, this is a symmetrical geometry, and this means that this guy is going to actually be nonpolar as well. And that's why in this case, the solvent is carbon tetrachloride with our Br2 because it is nonpolar, and nonpolar interacting with each other. They're both going to be using dispersion forces, and they're both going to be good. Again, if you try to put this in with water, what you would end up with is water that wants to use hydrogen bonding on the bottom, bromine that wants to use dispersion forces up on top, and you would get different layers. But here, when you put both of these guys together, it will mix perfectly because they're both using dispersion forces. So again, water is a common solvent but not always the right one for all the proper situations here. Like we talked about, that's that idea of like dissolves like in that particular case. All right, now you give that one a go. We're looking for two answers here. How many grams of KCl and how many grams of water in this solution here? Okay, so let's see how we're doing on this one. Again, there's a couple different ways you could do it. We're definitely dealing with percent mass to mass. So that is the percent mass to mass is our mass of solute divided by the mass of the solution times 100%. In this case, we do have the mass of the solution given to us, which is 225 grams. We also have the percent mass to mass given to us, which is 8%. So I'm going to approach this again as more of a conversion factor type approach. Again, you could do it the opposite way. So when it says 8% by mass potassium chloride, if I assume 100 grams, that means that I would have 8 grams of potassium chloride and 100 grams of solution. Again, coming from the percentage, just kind of converting it into a conversion factor. And again, I could get these two sort of conversions from this. Grams of KCl. So at this point, we do have the mass of the solution. So we would use the mass of the solution. And that would be 225 grams of solution. We would use it as a conversion factor here with the 100 grams of solution on the bottom, 8 grams of KCl on top. And that's going to give us times 8 divided by 100. Can give us 18 grams of KCl is in that solution, and that's the mass of the solute. Remember that the mass of the solution is the mass of the solute plus the mass of the solvent. So this is the mass of the solute we just found, and we did have the mass of the solution. So the mass of water, which is the solvent here, would be 225 grams minus 18. And that would get us something like 225. 207 grams of water would be put in there. Again, 207 grams of water, 18 grams of KCl gives us a grand total of 225 grams for the total solution. So the question was, can we do it the other ways? The other way is you would put the 8% in for mass equals the mass of KCl up on top. It would be 225 grams on the bottom times 100%. So it'd be just plugging it into the actual formula. And to solve this, you do basically the same math. You need to multiply the 2.25 to the other side. So that would give you 2.25 times 8% would equal the mass of the KCl times 100%. Then you would actually divide by 100%. Gets you over here to 100%. Those guys cancel, and you'll end up with the 18 grams of KCl. Mathematically, if you just look up on top there, you're basically doing the same thing. Sorry, it's not 2.25, it's 225. You have your 225 times 8, which is essentially what you did here. And then you're dividing by 100, which is essentially what you did here. The math is basically identical. It's just really your feeling as to how you want to kind of set it up. So it kind of works the same way. Sometimes people could kind of see the calculation easier with the conversion type aspect to it. Otherwise, it's just really rearranging the equation or the formula. But ultimately, it really is the same calculation math-wise as either way you sort of do it. So if you find one way is easier than the other, go with that way, and you should end up in the same spot. Other questions on percent concentrations? Okay. And here's just a table that kind of describes what we were talking about. That again, sometimes it's easier to kind of convert these things into conversion factors and kind of do it a more dimensional analysis approach. And sometimes it just kind of lines up things a little bit easier for you. Let's then talk about the really important unit of concentration, which is molarity. Molarity is the most common unit of concentration that you see with solutions. And molarity is really moles per liter. Molarity is abbreviated with a big M. So when you see a big M, it stands for moles per liter. And you could kind of think of it as a formula. Molarity is moles per liter. It really is moles of solute per liter of solution. Most people just call it moles per liter. So kind of like density is mass over volume, this equation here, or the formula for molarity, is oftentimes rearranged. And sometimes we need to solve for, say, liters. And if you solve for liters, liters would be the moles divided by the molarity. So that's a very common sort of rearrangement of that formula. And the most common one is a lot of times we will use the molarity and the liters to figure out the moles. The moles would equal the liters times the molarity. So that's sort of three versions of this equation. Molarity basically is this guy, but very common. We do rearrange it to solve for moles. We also rearrange it to solve for something like volume as well. And it is moles per liter. The number always goes with the moles part, and it's always like 1 liter. So when you see a number, so for example, if you see something that says 4.5 big M sodium chloride, that is read 4.5 molar sodium chloride. And basically what that means is you have 4.5 moles of sodium chloride per liter of solution. And you could really use it like a conversion factor as well. So you can in some cases use it just like it's written. If you needed to, you could throw the liters up on top and the 4.50 moles on the bottom. And again, use it more like a conversion factor as well. So, and that's basically doing some of this math here, dividing by it and stuff when you would do it. So when we say something is 1 molar, what that means is that is how many moles per liter there is dissolved in the solution. So when we look at something like 1 molar sodium chloride, really that means that we have 1 mole per liter of sodium chloride. And as we sort of did a little bit ago with our equivalents, when sodium chloride breaks apart into ions, we have 1 sodium ion and 1 chloride ion, which means if we do that conversion like we did with our equivalents, for every 1 mole of the whole thing, we get 1 mole of just the sodium ions. Those guys cancel. And if we were interested in just the ions of sodium, we could also say that it is 1 mole per liter of just sodium ions present. And if we did that for chloride, it would come out the same. We would say that there is in that solution 1 mole per liter of chloride ions that are present. So sometimes you're interested in the whole thing. Sometimes you're interested maybe in just the ions. So again, you can kind of use that mole to mole relationship to go from one to the next. It will be. We don't usually do that too much in here, but the question is, molarity is really moles per liter. And that usually is what you should probably keep in your head. If you take millimoles and divide it by milliliters, the 2 millis will cancel out and you will be left with molarity. So it's the exact same thing as long as you have millimoles on top and milliliters on the bottom. So sometimes people think if they take the milliliters and they multiply it by the molarity, they get moles. You actually don't get moles when you do that. You actually get what are known as millimoles. So as long as you take those millimoles and then divide by milliliters, everything works out okay. So you got to make sure they're both in that milli unit in order for it to work out okay in terms of that. But another way you can express sort of molarity is millimoles per milliliter. Most people don't express it that way because it's really the same thing as moles per liter. And that's usually what people look at. So before we end here, why don't we just try one really quick here together just to show you how we get there. So say we made a solution by dissolving 15.6 grams of KCl and enough water to make 1.25 liters. So if we think about the molarity, which is moles per liter, we basically need both of those things. So in terms of the liters part, we actually are already given it. So we have the bottom part. The top part we don't have, but we do have grams. So we should know at this point, right, if we need to go from grams to moles, we need the molar mass, right, from the periodic table. So if we go to the periodic table and look up KCl, K is 3910 grams per mole. Cl is 3545 grams per mole. And if we do that real quick here, 3910 plus 3545 gives us 74.55 grams per mole. Is it BR? I know, BR. See, is what happens when you rush. 7990, thank you for letting me know. All right, so we'll get the right numbers off the periodic table. That probably is going to make it come out much better, I think. 3910 on that. Let's go with 119. That sounds like a much better number there. 119 when you grab the right element off the periodic table. So we would have to convert these grams to moles, which is a common conversion that you need to do. 19 grams per mole. And if we do that, we would take 15.6 divided by 119, gets us 0.131 moles of KCl. We now have the top part that we need. So to find the molarity, we would divide it by the 1.25 liters. And if we do that, we will end up with 0.105. The units don't cancel, so it is moles per liter KCl. Or you could write it 0.105 big M KCl. So they're both perfectly fine. The big M stands for moles per liter, or you could just leave it as moles per liter. So it's very common to has to convert grams to moles and use the molar mass to do so. Any questions on that there? All right, so we will stop there today. One thing before half of you go out of here, we do have an exam coming up pretty soon after chapter 7. So a couple weeks or so from now. So just to make sure everybody's still on pace and all that good stuff, I think we're going to have a quiz next Wednesday on chapter 6. So we'll have a quiz next Wednesday. That's the gas chapter, I think. So we'll have a quiz on Wednesday on chapter 6, which should be gases, I believe. Yeah. So I don't know if it's going to be exactly in 2 weeks. We have to finish chapter 7. So I'll let you know on Monday for sure. We'll see where we are. I think we're probably finished 7 on Monday, but I'll let you know for sure. So for now, it's scheduled, I think, for 2 weeks from today. So I'll let you know definitely on Monday next week where we're at and when it will be. But we're definitely going to have a quiz next Wednesday on the gas chapter. That way, again, should hopefully keep you up to pace on everything. Other than that, I'm sorry I went a little bit long. Have a good lab if you're off the lab discussion. We'll start in about 5 minutes, give everybody a chance to stand up, and we'll start discussion in about 5. If you're out for the weekend, have a nice weekend. I'll see you next week. And if you're in discussion, I'll see you in about 5 minutes or so.